Welcome to the Deep Dive, presented by Knowledge Flow. Today, we're not just reviewing basic arithmetic. We're actually taking a fresh look at the fundamental architecture of numbers themselves. We're embarking on, well, a fascinating journey into the very foundations of mathematics. You might think of basic math as just, numbers and calculations, maybe something you learned way back in school, but it's so much more profound than that.
Oh, absolutely.
It's truly the universal language of the cosmos, you could say. The silent algorithm that governs everything from the spiral of a galaxy to, well, the patterns in your personal finances. Understanding its core principles isn't just about crunching numbers. It's like gaining a superpower for navigating, well, everything really, from daily decisions to the most complex scientific breakthroughs.
Precisely. Our mission in this deep dive is to unpack these fundamental concepts, starting from the simplest digits we use to count, moving through how they interact in complex equations, and then really exploring their myriad real-world applications. We'll simplify the essential rules that govern numerical operations, highlight some surprising connections between seemingly disparate mathematical ideas, and most importantly, equip you with the insights to understand why these basics matter so profoundly. You'll see how they underpin so much of what we experience, from the natural world around us to the digital structures that power our modern lives.
Okay, let's unpack this a bit. When we talk about numbers, beyond just, counting things, what's the deeper organizing principle? What's the fundamental idea behind them before we even start doing calculations? It seems so basic, but it feels like the very first crucial step.
It really is. And it's all about efficiency and universal representation. At its core, our number system is this highly organized and remarkably efficient method for writing truly vast quantities in a straightforward and, importantly, universally understandable way. This system, the one we primarily use today, relies on just 10 specific values. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9.
Or the 10 digits.
Exactly. These individual values are what we call digits. Think of them as the alphabet, maybe, of the quantitative world. And when we combine a group of these digits, we create what's known as a number. So, for instance, the number 345 is composed of 3 digits, 3, 4, and 5. This fundamental understanding that numbers, no matter how huge, are built from these basic single-digit blocks, that's where all our mathematical exploration truly begins. It's like an elegant shorthand for reality.
That immediately gives a new perspective. Okay, so once we have these foundational digits and numbers, how do we start to organize and categorize this, well, seemingly infinite collection of values?
Yeah.
Because it's clearly not just one big undifferentiated blob. There are distinct types of numbers with unique properties, right?
Oh, absolutely not a blob. And this categorization is crucial. It's crucial for understanding how numbers behave, how they interact, and ultimately how they can be applied in different contexts. We have several distinct categories, each with its own defining characteristics. They really help us make sense of the vastness of the number universe. First up, we have natural numbers.
Okay.
These are the ones we use for basic counting in everyday life. If you're counting apples or people or stars, you're using natural numbers. They're denoted by n and typically begin with 1.12345 and so on, extending infinitely. They're just what we naturally use to count discrete objects.
Makes sense.
Then we introduce whole numbers. Now, if we simply take that set of natural numbers and just add 0 to it, we form the set of whole numbers. These are denoted by WO 1, 2, 3, 4, 5.
So the only difference is adding 0.
That's the key distinction. All natural numbers are whole numbers, but the reverse isn't true because of that unique inclusion of 0. 0, of course, represents, the absence of quantity or maybe a starting point on a scale. Next, we can categorize numbers based on divisibility. We have even numbers. These are numbers that are perfectly divisible by 2, meaning they leave no remainder. They're denoted by E, 2, 4, 6, 8, 10, and so forth.
Got it.
And in contrast, odd numbers are, numbers that are not perfectly divisible by 2. 1, 3, 5, 7, 9, and so on. Now, this category is particularly fascinating. Prime numbers.
Right. I remember these being important.
They really are. Prime numbers are those numbers that are divisible by only 2 distinct positive divisors, 1 in themselves. Nothing else divides into them cleanly. So examples like 2, 3, 5, 7, 11, 13, 17, they're all prime numbers. This seemingly simple property makes them the fundamental atoms of multiplication, if you will. Every non-prime number can be built by multiplying primes together.
The building blocks.
Exactly. And a key insight here is that all prime numbers are odd, with one very unique and very important exception, the number 2. 2 stands alone as the only even prime number.
Why is that so significant?
Well, its uniqueness is fundamental to number theory. And maybe surprisingly, it even underlies the security of things like our online transactions through cryptography. It's a cornerstone.
Wow. Okay. That's a great connection. And speaking of prime numbers,
Yeah.
for larger numbers, how do you actually test if one is prime without, trying to divide it by every single number below it? There must be a smarter way.
Absolutely. There's a clever and much more efficient method, especially useful for larger numbers. If you want to check if a given number is prime, you don't need to test every number below it. No way. Instead, you first find an integer that is just slightly larger than the approximate square root of that number. Let's call this integer x for now.
Okay, the square root.
Right. Then you systematically test the divisibility of your number only by every prime number that is smaller than x. Not all numbers, just the primes smaller than x. If your number isn't perfectly divisible by any of those smaller prime numbers, then it is definitively a prime number. Otherwise, it's not. This massively reduces the number of checks you need to do.
Let's see that in action. Could you give an example?
Sure. Consider the number 349. Okay. First, find the approximate square root. The square root of 349 is about 18.68. So we need an integer larger than that. Let's just take 19. So x is 19. Now, list the prime numbers that are smaller than 19. Those are 17, 13, 11, 7, 5, 3, and 2. Now you test 349 against each of those primes. Is 349 divisible by 17? No. Remainder by 13? No. By 11? No. And so on down the list. Since 349 is not perfectly divisible by any prime number smaller than 19, we can definitively say 349 is a prime number. It's a really powerful method.
That is much faster. Okay, what other categories do we have?
Moving on, we have coprime numbers. Two numbers are considered coprime if their highest common factor, or HCF, is 1.
HCF. Highest common factor. Remind me.
That's the largest number that divides into both of them without a remainder. So if the HCF is 1, it basically means they share no common prime factors other than 1. For instance, the pair 9, 2. Factors of 9 are 1, 3, 9. Factors of 2 are 1, 2. The only common factor is 1, so they're coprime. Other examples, 5, 6, 11, 15. Notice they don't have to be prime themselves. 9 isn't prime, 6 isn't, 15 isn't. They just don't share any common prime factors.
Yeah, makes sense.
Then there are composite numbers. These are essentially all those numbers that are not prime numbers, with one crucial exception, the number 1. So examples include 4, which is 2 by 2, 6, 2 by 3, 8, 2 by 2 by 2, 9, 3 by 3, 10, 2 by 5, 12, and so on. It's important to remember that the number 1 is unique. It's neither prime nor composite. It's just 1, the multiplicative identity.
Okay, and we're still within the realm of positive numbers and 0 here. What about negatives?
Exactly. That brings us to integers. When we represent whole numbers using both negative and positive signs, these numbers are called integers. They're denoted by I or sometimes Z, and the set looks like -4, -3, -1, 0, 1, 2, 3, 4, extending infinitely in both directions on the number line.
Right, the number line.
Numbers appearing before 0 are called negative integers, and those appearing after 0 are positive integers. And 0 itself is unique again. It's neither positive nor negative. And it's worth noting, all the natural numbers and whole numbers we talked about, they are all automatically included within the set of integers. Integers give us a broader range, letting us represent things like temperature below 0 or dead.
Okay, that covers whole numbers, positive and negative. What about fractions?
Perfect lead-in. Next, we delve into the world of fractions with rational numbers. These are numbers that can be precisely represented in the form of PQ, where P and Q are both integers, and Q, the denominator, the bottom number, cannot be equal to 0 because, division by 0 is undefined.
Right, can't divide by 0.
Exactly. Examples include 23, -23, 1 out of 10, -110, 65. Even whole numbers like 7 can be written as 71. So any integer is also a rational number.
Ah, okay.
What's really fascinating about rational numbers is their density. Between any two rational numbers, no matter how close they seem, you can always find another rational number. In fact, you can find an infinite number of them. If A and B are two rational numbers and A is less than B, then A plus B2, their average, is just one example of a rational number that sits right between them.
Infinite density. Cool. So if those are rational numbers, what are the others?
The others are the irrational numbers. These are the numbers that cannot be represented in that simple PQ form, where P and Q are integers and Q isn't 0. Common examples are square roots of numbers that aren't perfect squares, like 2, 5, 7, 11.
Right.
Pi is the most famous example. It's the ratio of a circle's circumference to its diameter. While we often use approximations like 227 or 3.14.
Yeah, I use 3.14.
Those are just rational approximations. They're close, but they're not the exact value of pi. When pi is converted to a decimal, its digits go on forever after the decimal point without ever repeating in a pattern. That's the hallmark of an irrational number. Non-terminating and non-repeating decimal representation.
Forever and no pattern.
Yeah. And finally, we have the big umbrella category, real numbers. This represents the combination of all the rational numbers and all the irrational numbers we've just discussed. So the set of real numbers includes integers, natural numbers, whole numbers, fractions, terminating decimals, repeating decimals, and those non-repeating, non-terminating decimals like pi and t2. They form that continuous line of values that we use for pretty much all practical measurements, calculations, and graphing on a standard number line. It's the whole numerical canvas we usually work with.
That's a fantastic overview, really maps out the numerical landscape. But when we actually start calculating, especially with fractions, these numbers often turn into decimals. How do these classifications, rational versus irrational, play out when we perform that kind of division?
It's actually quite straightforward, and it ties directly back to that rational-rational distinction. When you convert a rational number, remember, one that can be written as PQ into its decimal form, one of two very predictable things will happen. First, the division might end cleanly. The digits after the decimal point stop. These are called terminating decimals.
Like 1 divided by 2 is 0.5. It just stops.
Exactly. Or 1 divided by 5 equals precisely 0.2. Or 5 divided by 4 equals 1.25. In all these cases, the decimal representation concludes after a finite number of digits. The calculation terminates. The second possibility for a rational number is that the digits after the decimal point go on forever, but they start repeating in a pattern. These are called non-terminating decimals that repeat.
Okay, like 1 divided by 3.
Perfect example. 1 divided by 3 results in 0.333, where the digit 3 just keeps repeating endlessly. Another one could be, say, 69 divided by 550. If you calculate that, you get 0.125454454, where the sequence 54 keeps repeating itself over and over.
And I've heard the term recurring decimals, too. Is that the same thing as non-terminating repeating?
Yes, exactly. Recurring decimals is just another common term for these non-terminating decimals, where the digits after the decimal point repeat in a cycle. So 0.333 for 13 is definitely a recurring decimal. The key distinction we want to really nail down here is that all rational numbers, when converted to decimals, will either terminate or recur. Irrational numbers, like pi or shed2 on the other hand, result in decimals that are both non-terminating and non-repeating. That's what fundamentally sets them apart in their decimal form, that endless, patternless sequence of digits.
That clarifies the decimal connection perfectly. Now, this raises a practical point, especially when dealing with division or factors. How can we quickly tell if one number divides another without doing the whole long division calculation? Are there quick tests for divisibility we can use, like mental shortcuts?
Absolutely. These divisibility tests are fantastic mental shortcuts. They can save you a lot of time and effort, especially with larger numbers. They let you rapidly assess divisibility without the full calculation. Think of them as little number tricks.
Okay, let's hear them.
All right. Divisible by 2. Super easy. A number is divisible by 2 if its last digit is an even number. 0, 2, 4, 6, or 8. Just look at the last digit. Divisible by 3. A number is divisible by 3 if the sum of all its individual digits is divisible by 3.
Example.
So, take 123, add the digits 1 plus 2 plus 3 equals 6. Is 6 divisible by 3? Yes. So 123 is divisible by 3. Or 567, 5 plus 6 plus 7 equals 18. Is 18 divisible by 3? Yes. So 567 is 2.
Neat trick. Why does that work?
It has to do with the properties of our base 10 system and remainders when dividing powers of 10 by 3. Basically, the sum of the digits carries the same divisibility by 3 property as the original number.
Interesting. Okay, what's next?
Divisible by 4. A number is divisible by 4 if the number formed by its last 2 digits is divisible by 4. So for a big number, like, say, 7,893,216, you only need to look at the 16. Is 16 divisible by 4? Yes. So the whole huge number is divisible by 4.
Because anything before that is hundreds, thousands, etc., which are all divisible by 4 anyway.
Precisely. 100 is divisible by 4, so you only need to check the remainder part, the last 2 digits. Divisible by 5, even easier than 2. A number is divisible by 5 if its last digit is either 0 or 5. That's it.
Okay.
Divisible by 6. This one combines 2 previous rules. A number is divisible by 6 if it meets the criteria for being divisible by both 2 and d3. So it must be an even number. Last digit 0, 2, 4, 6, or 8, and the sum of its digits must be divisible by 3. You have to check both conditions.
Got it. Both 2 and 3.
Divisible by 8. Similar logic to the rule for 4, but extended. A number is divisible by 8 if the number formed by its last 3 digits is divisible by 8. This works because 1,000 is divisible by 8. So for a number like 54,128, you check if 128 is divisible by 8. It is 128, 8 equals 16. So 54,128 is divisible by 8.
3 digits for 8, 2 digits for 4.
Okay. Divisible by 9. This rule is very similar to the rule for 3, but stricter. A number is divisible by 9 if the sum of all its individual digits is divisible by 9. Example. 729, sum of digits. 7 plus 2 plus 9 is 18. Is 18 divisible by 9? Yes. So 729 is divisible by 9. It works for the same base 10 reasons as the rule for 3.
Okay. Sum of digits for 3 and 9, but divisible by 3 or 9, respectively.
Correct. And finally, divisible by 11, this one's a bit more involved, requires a small calculation. A number is divisible by 11 only if the difference between the sum of its digits at odd places, counting from the right, and the sum of its digits at even places, also counting from the right, is either 0 or a multiple of 11.
Whoa, okay. Walk me through that.
Let's take the number 9482, odd places from right. First digit is 2, third digit is 4, sum is 2 plus 4 equals 6, even places from right. Second digit is 8, fourth digit is 9, sum 8 plus 9 equals 17. Now find the difference. 17, 6 equals 11. Since the difference is 11, which is a multiple of 11, the original number 9482 is divisible by 11. If the difference was, say, 5 or -3, it wouldn't be. It has to be 0 or a multiple of 11.
That's intricate but very cool. These tests are genuinely useful shortcuts. So we've mapped out the incredible variety within the world of numbers. But numbers aren't just for classifying, right? They're for doing things. How do these different types start to interact when we perform operations? Especially something as fundamental as dividing a whole into parts, which brings us straight to fractions.
That's a perfect transition. Fractions are absolutely foundational. They're how we represent parts of a whole, and understanding their mechanics is crucial for everything from, well, baking a cake accurately to complex engineering calculations. A fraction, formally, is any number that can be expressed in the form PQ, where P is called the numerator, that's the top number representing the parts we have,
Right.
and Q is the denominator, the bottom number, representing the total number of equal parts the whole has been divided into. And crucially, as we mentioned with rational numbers, the denominator Q cannot be 0. Division by 0 is undefined in mathematics. So, for example, in the fraction 45, 4 is the numerator, 5 is the denominator. It means 4 parts out of a total of 5 equal parts.
Okay, basic fraction definition. But what about when we have multiple operations involving fractions, or any numbers really? How do we know what to do first?
Yes. Order of operations. This is absolutely key to getting the right answer consistently. When dealing with fractions, or really any mathematical expression with multiple operations, understanding how they are simplified is critical. This brings us to the process of simplification, which defines the precise order you must follow. When you encounter a calculation with multiple things happening simultaneously, maybe brackets, addition, subtraction, multiplication, division, you have to follow the BODMS rule strictly.
BODMS. I remember that acronym. Can you break it down?
Sure. BODMS stands for B for brackets. You always deal with anything inside brackets first. O for orders. This includes things like powers, like squaring or cubing, or roots, like square roots. D for division. M for multiplication. Note, division and multiplication have equal priority and are done from left to right as they appear.
Oh, okay. Left to right for D and M.
Yes. Then A for addition, and S for subtraction. Again, addition and subtraction have equal priority and are done left to right. Problems must be solved following this exact sequence. Brackets, orders, division, multiplication, addition, subtraction. For example, if you see 2 plus 3, 4, you don't do the addition first, 2 plus 3, 5, and then multiply by 4 to get 20. No. You follow BODO DMA. Multiplication comes before addition. So you do 3, 4 equals 12 first, then you do 2 plus 12 equals 14.
Got it. That prevents getting different answers from the same problem.
Exactly. It ensures consistency. And furthermore, when simplifying expressions with nested brackets, like brackets inside other brackets, you must also follow an order. Typically, you start with the innermost brackets and work your way outwards. This whole hierarchical approach ensures complex expressions give one single, unambiguous result, like following a recipe precisely.
Makes sense. Now, building on the idea of factors and multiples, which we touched on with prime numbers,
Right.
how do we find common relationships between numbers, like their largest shared factor or their smallest shared multiple? These seem abstract, but I feel like they pop up a lot.
They absolutely do pop up a lot. These concepts, highest common factor, HCF, sometimes called greatest common divisor or GCD, and least common multiple, LCM, are foundational. They're essential for working with fractions, especially finding common denominators, but also for solving a whole range of problems involving measurement, scheduling things, even in computer science for algorithms. Let's start with the highest common factor, HCF. The HCF of 2 or more numbers is the largest number that divides into all of them without leaving a remainder. It's the biggest factor they have in common.
Okay, largest common divisor. How do we find it?
There are 2 main methods. The first is the factorization method. Here, you break down each number into its prime factors. Remember those building blocks.
Right.
Then you look for the prime factors that are common to all the numbers in your set. You multiply these common prime factors together, making sure to use the lowest power of each common factor that appears in any of the factorizations.
Lowest power. Okay, can we see an example?
Sure. Let's find the HCF of 336, 240, and 96. First, prime factorize each. 336 is 2a2, a2, 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 a3, a3, s7. That's 24 to a3, s7. 240 equals 2, a2, a2, a3, a5. 96 was 2, a2, a2, a2 to a3. That's 25 to a3. Now look for the common prime factors. All three numbers have the prime factor 2. All three also have the prime factor 3. They don't all share 7 or 5. For the common factor 2, what's the lowest power that appears? We have 24, 24, and 25. The lowest is 24. For the common factor 3, the lowest power is just 31. It appears once in each. So the HCF is 24, 2, a2, a3, s3, a3, 3, a3, a16, s3 equals 40. 48 is the largest number that divides evenly into 336, 240, and 96.
Okay, prime factors. Find the common ones, use the lowest power. Got it. What's the other method?
The second is the division method. This uses successive division and remainders. It's often quicker for just two numbers, or it can be chained for more. Let's quickly find the HCF of, say, 36 and 54 using this. Divide the larger number, 54, by the smaller 36. 54 divided by 36 is 1 with a remainder of 18. Now divide the previous divisor, 36, by that remainder 18. 36 divided by 18 is 2 with a remainder of 0. As soon as you get a remainder of 0, the last divisor, which was 18, is the HCF. So HCF 3654 equals 18. To extend this to three numbers, like finding HCF of 36, 54, and 63, first find HCF 3654, which we found is 18. Then find HCF 1863. Divide 63 by 18 goes 3 times, remainder 9. Divide 18 by 9 goes 2 times, remainder 0. So the final HCF is 9.
Okay, two methods for HCF. What about the LCM, the least common multiple?
Right, the least common multiple, LCM. The LCM of two or more numbers is the smallest non-zero number that is a multiple of all of them. It's the smallest number that all the original numbers can divide into evenly.
Smallest number they all go into, useful for fractions, right? Common denominator.
Exactly. That's probably its most common application. Again, we have two main methods. First, the factorization method for LCM. Again, start by breaking down each number into its prime factors. This time, however, you take all unique prime factors that appear in any of the numbers, and for each unique factor, you use the highest power that appears in any single factorization.
Highest power this time.
Okay.
An example.
Let's find the LCM of 24, 16, and 40. Prime factorize. 16 equals 2, dive 2, dive 2, dive 2, dive 2 is 24. 24 equals 23, dive 31. 40 is 2, dive 2 by 5 equals 23, dive 51. Now, what are all the unique prime factors involved across these numbers? We see 2, 3, and 5. For the factor 2, what's the highest power we see? It's 24 from the 16. For the factor 3, the highest power is 31 from the 24. For the factor 5, the highest power is 51 from the 40. So the LCM is the product of these highest powers. 24, I have 31, or 51 is 16, I have 3, I have 5 equals 240. 240 is the smallest number. The 16, 24, and 40 all divide into evenly.
Okay, factorization for LCM. All unit primes, highest power. What's the division method like for LCM?
The division method for LCM is often done using a sort of table or ladder format. You arrange the numbers, say 84, 56, 63, and start dividing them by common prime factors. You divide by 2 if possible, hitting 84 and 56. Bring down any numbers not divisible. Repeat with 2, then try 3, then 7, etc., until no two numbers share a common factor. The LCM is then the product of all the prime divisors you used on the side and the remaining numbers at the bottom. For 84, 56, and 63, this process would yield an LCM of 504.
Those methods are clear. Can you give us some practical illustrations now? How are HCF and LCM actually used to solve word problems?
Certainly. They translate directly into solving certain types of problems. Example 1. What is the smallest number from which, on subtracting 5, the remaining number is divisible by 16, 18, 20, and 24?
Okay, how do we approach that?
The core logic is, if a number after you subtract 5 is perfectly divisible by 16, 18, 20, and 24, then that resulting number, the number minus 5, must be a common multiple of all those divisors. And since we want the smallest such original number, the result after subtraction must be the least common multiple, LCM. So find the LCM first.
Exactly. Calculate the LCM of 16, 18, 20, and 24. Using one of the methods, you'll find the LCM is 720. But the question asks for the original number, the one before subtracting 5. So you just add the 5 back to the LCM. 720 plus 5 equals 725. So 725 is that smallest number. If you subtract 5, you get 720, which is divisible by 16, 18, 20, and 24.
Clever. Okay, another one.
Example 2. What is the smallest number which, when divided by 20, 25, and 30, leaves remainders of 8, 13, and 18 respectively.
This looks different. Remainders.
It is different, but often these problems have a pattern. Look at the difference between each divisor and its corresponding remainder. 20 divisor, 8 remainders, 12. 25 divisor, 13, remainder equals 12. 30 divisor, 18, remainder 12.
The difference is the same. It's 12 in every case. Exactly. When you see this consistent difference, the required number will be the LCM of the divisors, 20, 25, 30, minus this common difference, 12. First, find the LCM of 20, 25, and 30. That comes up to 300. Now, subtract the common difference. 312 equals 288. So 288 is the smallest number that fits the conditions. Let's check. 288.20 is 14 with remainder 8. 288.25 is 11 with remainder 13. 288.30 is 9 with remainder 18. It works. That pattern is the key.
That's really neat. Okay, moving on slightly. These next concepts, surds and indices, they seem to deal with how numbers relate to themselves through multiplication, like repeated multiplication or going backwards from that. This is where things like scientific notation come from too, right?
Exactly. We're moving into powers and roots, which give us incredibly powerful tools. They let us express very large or very small numbers compactly, and they're essential for solving problems involving growth, decay, and many geometric relationships. Let's start with surds. Basically, surds are roots of quantities that cannot be simplified down into a nice, neat, rational number. Precisely. Sur2 or de3 are classic examples of surds. Their decimal forms go on forever without repeating. They're irrational, so you can't write them as a simple fraction PQ. But surd still represents an exact, specific value on the number line. It's just irrational. We call such root expressions surds. While we won't dive deep into all the specific rules of surds today, like how to add 2 and 2, 8, it's important to know they exist. These rules allow us to manipulate these unsimplifiable root numbers rigorously in calculations, especially in geometry and algebra.
Okay, so surds are messy roots. What about indices?
Indices, or exponents, or powers are the opposite side of the coin. They provide a concise way to represent repeated multiplication. If you multiply a number x by itself n times, so x, repeated n times, we write it shorthand as xn. This is read as x to the power n, or x raised to the nth power. Here, x is called the base, the number being multiplied, and n is the index or exponent telling you how many times to multiply the base by itself.
Like 23 means 2 times 2 times 2.
Exactly. 23 equals 2, 2r2 equals 8. Just like surds, there's a whole set of rules of indices that dictate how you combine, simplify, and manipulate expressions involving exponents. These rules are fundamental in algebra and beyond.
Can you give an example of a rule?
Sure. One of the most basic is when you multiply numbers with the same base, you just add their exponents. So Zac xb equals xa plus b. For instance, 2324 doesn't equal 212. It equals 23 plus 4 equals 27.
That simplifies things a lot.
Immensely, especially in science dealing with huge numbers, or in computer science calculating things like memory or processing power. These rules are workhorses.
Okay, so indices are for repeated multiplication. How do we reverse that process? How do we find the original number that when multiplied by itself, say twice or 3 times, gives us the number we're looking at?
That's precisely where square roots and cube roots come into play. They are the inverse operations of squaring, raising to the power of 2, and cubing, raising to the power of 3, respectively. They let us undo that repeated multiplication. The square root of a given number is that number which, when multiplied by itself, yields the original number. We denote it with the symbol a. For example, the square root of 16 is 4, because 4 by 4 equals 16. We write 16 equals 4.
And how do we find square roots, especially if they aren't obvious like 16?
There are primarily 2 methods we learn. The factorization method works nicely for perfect squares. You factorize the number completely into its prime factors, then you group the identical factors in pairs. For every pair of identical factors, you take just one of them out, multiply all the factors you took out, and that product is your square root.
Example.
Let's find the square root of 900. Prime factorization of 900 is 2i2 by 3 by 3 by 5 by 5. Now group the pairs, 2i3 by 3 by 3 by 5 by 5. Take one factor from each pair, 1, 2, 1, 3, 1, 5. Multiply them together. 2i3 by 5 is 30, so 900 equals 30.
Okay, that works well for perfect squares. What if it's not a perfect square, or it's a really large number?
That's where the division method comes in. It's a more systematic algorithm, a bit like long division, that lets you find the square root digit by digit. It's particularly useful for larger numbers or for finding decimal approximations of non-perfect square roots. While the detailed steps are a bit intricate to explain fully without visuals, it's a reliable process. For instance, applying the division method to find the square root of 998,556 would correctly yield 316.
Okay, a more general method. What about cube roots?
The cube root follows similar logic. The cube root of a given number is that number which, when multiplied by itself 3 times successively, yields the original number. We denote it with a slightly different symbol. For instance, the cube root of 8 is 2, because 2 is 2 arrow 2 equals 8. We write oop equals 2.
And how do we find cube roots? Is there a similar factorization method?
Yes, the factorization method is the primary method used here too. You factor the number into its prime factors, just like before, but this time, instead of pairs, you form groups of 3 identical factors, triplets. Then you take one number from each group of 3 and multiply them together. The result is the cube root.
Let's try one. How about 1728?
Okay, 1728. Let's factorize it. 1728, let's factorize it. 1728 equals 2 die 2 die 2 die 2 die 3 are 3. Now group into triplets of identical factors. 2 die 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 3 die 3 die 3. Take one factor from each triplet, 1 2, another 2, and 1 3. Multiply them. 2 die 2 by 3 equals 12. So 1728 equals 12.
Neat. These methods really let us reverse those power operations. Okay, now let's explore how we find unknown values. This really feels like the heart of algebra and problem solving in math, doesn't it? Where the numerical structure meets logic to find missing pieces. We should probably start with the simplest type, linear equations.
You've hit on it exactly. Linear equations are sort of the entry point into solving for unknowns. They are defined as equations where the variable, the unknown value we're trying to find, usually represented by a letter like x or y, has a power of 1. This means you won't see terms like x squared or y cubed. The variables just appear simply as x or y. For instance, equations like 4x plus 2 equals 5 or 2y 2 equals 4. These are both linear because the x and y each have that implied power of 1. They represent direct, straightforward relationships, often a straight line if you graph them.
Okay, power of 1. And can they have different numbers of variables?
Yes, we categorize them that way. A linear equation in one variable is exactly what it sounds like. There's only one type of unknown involved. For example, in the equation 3x plus 5 plus 5, 7, x is the sole variable we need to solve for. You simply use inverse operations like subtracting 5 from both sides, then dividing by 3 to isolate x. It's like balancing a scale.
Pretty straightforward. What about 2 variables?
Then you have linear equations in 2 variables. These equations naturally involve 2 distinct variables, most commonly x and y. Examples would be 2x plus 3y equals 4, or 7x plus 2y equals 5. Now, here's a really important principle. To find unique values for 2 variables, you generally need to have 2 separate equations that relate them.
One equation isn't enough.
Not for a unique solution. If you only have one equation with 2 unknowns, like x plus y equals 10, there are infinite pairs of x and y that could work. 1 and 9, 2 and 8, 0 and 10, might occur 1 and 11, even fractions. It has infinite solutions. For an optimal or unique solution, the number of independent equations must match the number of variables you're trying to solve for. 2 variables need 2 equations, 3 variables need 3 equations, and so on.
Okay, that's crucial. So if we do have 2 equations and 2 variables, what are the common methods to actually find that specific pair, x, y, that makes both equations true? That sweet spot.
Right, solving the system of equations. There are 2 widely used and effective methods for linear systems. The first is the elimination method. The whole idea here is to strategically manipulate the equations to eliminate one of the variables, letting you solve for the other one first.
How does that work?
Let's take an example system. Equation 1, 2x plus 3y equals 12. Equation 2, 5x plus 2y equals 19. Our goal is to make the coefficient, the number in front, of one variable, say x, the same in both equations, but maybe with opposite signs. We can multiply equation 1 by 5 and equation 2 by 2. Watch 2x plus 3y equals 12. F5 gives us minus 10x plus 15y equals 60. Let's call this I. 5x plus 2y equals 19. X2 gives us minus 10x plus 4y equals 38. Let's call this 2.
Now both have 10x.
Exactly. Now, if we subtract equation 2 from equation I, the 10x terms will cancel out, eliminating x. 10x plus 50y, 10x plus 4y equals 60, 38. 10 by 10x is 0, 15y, 4y is 11y, 60, 38 is Tomo 2, so we're left with 11y equals 22, much simpler. And that means y equal. Precisely. Now that we have y equal 2, we substitute this value back into either of the original equations to find x. Let's use equation 1. 2x plus 3, 2 equals 12. 2x plus 6 equals 12. Subtract 6 from both sides, 2x equals 6. Divide by 2, x equals 3. So the unique solution to this system is x3 and y equals 2. That's the elimination method.
Okay, eliminate one variable, solve for the other, then substitute back. What's the second method?
The second method is the substitution method. This approach involves solving one of the equations for one variable in terms of the other, and then substituting that expression into the second equation.
In terms of the other, like get x something with y.
Exactly. Let's use a different example system. Equation y, 3x plus 2y equals 16. Equation 2, 7x plus y equals 19. Look at equation 2. It's really easy to solve for y. Just subtract 7x from both sides. Y equals 19 7x. Let's call this equation 3. Now we have an expression for y. We substitute this entire expression, 19 7x, in place of y in the other original equation, equation 1. 3x plus 2, 19 7x equals 16.
No, that equation only has x in it.
Right. Now we solve for x. Distribute the 2.3x plus 38, 14, x equals 16. Combine the x terms. 3 by 14x is 9-11x. So 9-11x plus 38 equals 16. Subtract 38 from both sides. 9-11x equals 16. 38 equals 9-22. Divide by 9-11 equals 2. Now we have x equals 2. Substitute this value back into our handy equation 3 to find y equals 19.72, y equals 19.14, y equals 5. So the solution using substitution is x equal 2 and y equals 5. Both methods are equally valid. Sometimes one is just a bit easier depending on how the equations look.
That's a really clear breakdown of handling linear equations. But this raises an important question. What happens when the variable's power changes? Specifically when it goes up to a power of 2. This brings us to quadratic equations, which, if I remember correctly, often give us multiple answers, not just one.
You remember correctly, it does open up a whole new world of solutions. Quadratic equations are defined by having a variable with a power of 2 and no higher powers like cubed or power 4. The typical or standard form we write them in is x2 plus bx plus c cannot be 0.
Why can't a be 0?
Because if a were 0, the x2 term would just disappear, and you'd be left with bx plus c equals 0, which is just a linear equation again. So the x squared term is essential for it to be quadratic. Now, a key characteristic, a fundamental insight about quadratics is that when you solve them, you will always find two values for the variable x.
Always 2.
Always two solutions, or roots, as they're called. These values are often denoted by the Greek letters L, alpha, and beta. Now, those two roots might sometimes be the same number, a repeated root, or they might be two distinct numbers. Geometrically, if you graph the equation y equals x2 plus bx plus c, the roots are the x values where the parabola, that U-shape, crosses the x-axis. So you can cross twice, touch once, repeated root, or potentially not cross at all in the real numbers.
Okay, two roots. How do we find them? Is there a factorization method like before?
Yes, there is. The factor method is one approach. If you can factor the quadratic expression x by 2 plus bx plus c into two linear factors, you can easily find the roots. Let's find the roots of by 2, 5x plus 6 equals 0 using this method. Here, a 1, b minus 5, and c equals 6. We need to find two numbers that multiply to c, which is 6, and add up to b, which is minus 5.
Multiply to 6, add to minus 5. That would be minus 2 and minus 3.
Exactly. Minus 2, minus 3 plus 6 and minus 2 plus minus 5. Perfect. So we can rewrite the equation by splitting that middle term using minus 2 and minus 3 by 2 by 3x plus 6 equals 0. Now we factor by grouping the first two terms and the last two terms, x by 2, 3 by 2, b equals 0. Notice the x2 is a common factor now, so we can factor it out. By a 2 by 3 equals 0. Now for this product of two things to be 0, one or both of them must be 0. So either by 2, x at x, which means x equals 2, or by 3 is 0, which means x equals 3. Those are our two roots, x2 and x equals 3.
Factoring works well when you can spot the numbers. What if you can't, or if the numbers are messy?
That's where the second method comes in, and this one is universally applicable. It's the formula method, using the famous quadratic formula. For any quadratic equation in the form x2 plus bx plus c equals 0, the solutions, the roots, can be found directly using this formula. X equals now B2 4A C2A.
Ah, yes, the quadratic formula. That plus minus sign is why we get two answers, right?
Precisely. You calculate the value once using the plus sign and once using the minus sign to get your two roots, alpha and beta. Now, within this formula, there's a really important part. The expression under the square root sign, B2 4AC. This specific quantity has a special name. The discriminant.
Discriminant? Why is it special?
Because its value discriminates between the different types of roots you can get, even before you finish solving the whole formula. It's like a little fortune teller for your quadratic equation. Here's what the discriminant tells you. If B2 4AC x is 0, the discriminant is 0, then the square root part becomes 0, 0. The 0 doesn't change anything, so you get only one value for x, and that's just B2A. This means the roots are equal, or it's a single repeated root. The parabola just touches the x-axis.
Okay, discriminant 0 equal roots.
If B2 4AC 0, the discriminant is positive, then you're taking the square root of a positive number, which gives you a real value. The Namek means you'll get two different answers. Nebi B plus the root 2A and Nebi the root 2A. So the roots will be unequal and real numbers. The parabola crosses the x-axis at two distinct points.
Discriminant positive, two different real roots.
And if B2 4x0, the discriminant is negative, then you're trying to take the square root of a negative number. In the realm of real numbers, you can't do that. This means the roots will be unequal, but unreal. They involve imaginary numbers called complex numbers. The parabola completely misses the x-axis.
Discriminant negative complex roots.
Yeah.
Got it. That's actually very informative just from one part of the formula.
It really is. And one more useful thing about roots. For any quadratic equation, x2 plus bx plus c equals 0 with roots I f e, there are simple relationships between the coefficients a, b, c and the roots. The sum of the roots, I plus a, always equals nev b, and the product of the roots, I f e, always equals k.
How is that useful?
It's great for checking your answers. After you find the roots using the formula or factoring, you can quickly add them and multiply them to see if they match EBA and CAC. It's also useful if you know the roots and want to construct the quadratic equation itself.
Okay, let's see these powerful equation types, linear and quadratic in action, with some practical problems. How do they help us unravel unknown values in, more word-based scenarios?
Great idea. Applying them helps solidify the concepts. Example 1, a 2-digit number problem. Let's revisit that. A 2-digit number is such that the tens place digit is 2 less than the unit place digit. The sum of 3 times the number and 67th of the number formed by reversing the digits is 108. What is the sum of the digits of the number?
Okay, lots of words. How do we translate that?
First, represent the unknown digits. Let the unit place digit be x and the tens place digit be y. How do we write the value of a 2-digit number using x and y? The tens digit has a value of 10y. The units digit has a value of x. So the number is 10y plus x. Like if y 3 by 5 number is 35.
Right, place value.
Now, translate the conditions into equations. Condition 1, tens place digit y is 2 less than the unit place digit x. So y equals by 2, or equivalently x equals y plus 2. Let's keep that handy. This is a linear relationship. Condition 2. The sum of 3 times the number and 67th of the number formed by reversing the digits is 108. 3 times the number is 310y plus x.
Right.
Number formed by reversing the digits means swap x and y, so the reverse number is 10x plus y. 67th of the reverse number is 67, 10x plus y. The sum is 108, means 310y plus x plus 67x plus y equals 108.
Okay, now we have 2 equations involving x and y. One linear, one looks more complicated.
It is. We have y equals 2, or x equals y plus 2, and that second big equation, we can use substitution. Substitute x equals y plus 2 into the second equation. It will get messy, involving fractions, but after simplifying and solving that resulting linear equation for y, you would find that y equals 2. Once you have y2, substitute it back into x, y plus 2 to find x2 plus 2 plus 4. So the original number, 10y plus x, is 10. 2 plus 4 equals 24. The question asks for the sum of the digits. X plus y, that's 4 plus 2 equals 6. See how we use linear equation concepts, setting up relationships, substitution to solve it.
Actually, step by step. Okay, how about a quadratic example?
Example 2. Number and its square problem. When 4 times a number is subtracted from 3 times the square of the same number, the value obtained is 50 more than the number. What is the number?
Okay, let the number be x.
Good start. Now translate the phrases. 4 times a number is 4x. 3 times the square of the same number is 3 by 2. 4 times a number is subtracted from 3 times the square. Means 3 by 2, 4x. The value obtained is 50 more than the number, means the result equals x plus 50. So putting it all together, 3 by 2, 4x plus 50.
And that looks like it's going to be quadratic once we rearrange it.
Exactly. Move all terms to one side to set it equal to 0, the standard form. 3 by 2, 4x by 50 equals 0. Combine the x terms. 3 by 2, 5 by 50 equals 0. Now we have a quadratic equation. We can try to factor it or use the formula. Let's try factoring. We need 2 numbers that multiply to AC, which is 3 to 50, lenish 150, and add up to B, which is netish 5.
Multiply to negative 150, add to negative 5, maybe negative 15 and plus 10.
Perfect. Negative 15, 10, negative 150, and negative 15 plus 10 by negative 5. So we split the middle term. 3 by 2, 15x, plus 10 by 50 is 0, 0. Factor by grouping. 3x by 5 plus 10 by 5 equals 0. Factor out the common by 5 by 5. 3x plus 10 equals 0. This gives 2 possible solutions. Either by 5 equals 0, so x plus 10 equals 0, so 3x plus 10 is 10, which means x equals 103.
2 answers. Does the question imply which one?
Usually when a problem just says a number, it implies a positive integer or at least a real number used in typical counting contexts. So while both are mathematically valid roots, the most likely intended answer is x plus 5.
Okay, one more. Let's find the roots and check their nature for a specific equation.
Example 3. Finding roots and nature of roots for by 2, 7x plus 12 less 12.
Okay, A1, B7, C12. Let's use the formula this time.
All right. X, B says B, A, C, B, B2, 4AC, 2A. Substitute the values. X, negative 7, 2, 4S, 1, 12, 2, 1. Simplify inside. X equals 7 minus 7, 31, 48. 2 point X equals 7 minus 1, 2. X equals 7 minus plus 1, 2. Now the two roots using the y9 is root 1 using plus bet x minus 7 plus 1, 2 equals 8, 2 equals 4. Root 2 using this x1, 2 equals 6, 2 equals 3. So the roots are 4 and 3.
And what about the nature of the roots? We use the discriminant, right?
Yeah,
B2 for SC.
Calculate it. B2 for AC and equals 7, 2, 4, 20 next 1 minus 4 equals 1. The discriminant is 1. What does that tell us?
It's positive,
That's
0.
wrong.
So the root should be unequal and real.
Which matches perfectly with the roots we found. 4 and 3 are definitely unequal in real numbers. The discriminant confirms the nature of our solution.
Solving for the unknown is clearly fundamental. But often the unknown isn't just a single number, is it? Sometimes it's about the relationship between multiple quantities. This brings us to how we compare and relate different numbers, leading us to concepts like ratios, proportions, and percentages, which feel very practical.
Precisely. These tools allow us to express how quantities stand relative to one another. They make complex relationships understandable and, importantly, comparable, even when the underlying numbers are very different. Let's start with ratio. A ratio is fundamentally a comparison of how many times one quantity contains another quantity of the same kind. It's essentially showing the fractional relationship between them. The ratio 2 to 3 can be written with a colon, 2.3, or as a fraction, 23. In any ratio AB, A is the first term, sometimes called the antecedent, and B is the second term, the consequent. But really, it's just comparing the first quantity to the second. How much of A for every unit of B?
Okay, comparing two things. Can we combine ratios?
Yes, you can form a compound ratio. This is done by multiplying together all the antecedents, the first terms, from several ratios to get a new combined antecedent, and similarly multiplying all the consequents, second terms, to get a new combined consequent. For example, if you wanted the compounded ratio of 4.3, 9.13, 26.5, and 2.15, it sounds complicated, but you just calculate 4a, 9a, 26a2 for the first part and 3a, 13, 5a, 15 for the second part. This gives a single ratio representing the overall multiplicative relationship.
Okay. Are there other special types of ratios?
There are a few terms you might encounter related to a basic ratio, AB. B2 is called the duplicate ratio, like squaring both parts. AA is a subduplicate ratio, square root of both parts. A31B is the triplicate ratio, cubing both parts. AAB, or A13, is the subtriplicate ratio, cube root. And 1A, 1D is simply the inverse ratio or reciprocal ratio.
Duplicate, triplicate, okay. Now what about proportion? How does that relate to ratio?
Proportion is simply when two ratios are equal. They represent the same relative comparison. For example, consider the ratio 6.18. That simplifies to 1.3, right?
Yes, 6 is 1/3 of 18.
Now consider the ratio 8.24. That also simplifies to 1.3. Since both ratios are equal, both 1.3, we say they are in proportion. We can write this equality as 6.18.8.24.
That double colon means is proportional to or as.
Exactly. It reads 6 is to 18 as 8 is to 24. It signifies an equality between the two ratios. And there's a specific case called continued proportion. This applies when you have three quantities, say A, B, and C, where the ratio of the first to the second is equal to the ratio of the second to the third.
Right.
So A, B, B, C. In this setup, B, the middle term, is called the mean proportional between A and C. And C, the last term, is called the third proportional to A and B. This structure comes up a lot in geometry, particularly with similar shapes.
Mean proportional, third proportional. Okay. These seem like powerful tools for relating quantities. Can you walk us through some practical illustrations? How are ratio and proportion actually used to solve problems?
Of course. These concepts are woven into many problem-solving contexts, from simple division to more complex comparisons. Example 1. Dividing a quantity in a given ratio. This is very common. Let's say you need to divide $1,458 or units or anything in the ratio 2.7.
How do we split it?
First, find the total number of parts in the ratio. 2 plus 7 equals 9 parts in total. The first share corresponds to 2 out of these 9 parts. So the first part is 29 of the total amount. 1458 equals 324. The second share corresponds to 7 out of the 9 parts. So the second part is 79 of 1458 equals 1134. And you can check 324 plus 1134 equals 1458. So 1458 divided in the ratio 2.7 gives you 324 and 1134. Useful for splitting profits, ingredients, anything really.
Straightforward enough. What about a slightly more algebraic one?
Example 2. Numbers in a ratio with sum of squares. 3 numbers are in the ratio 1.2.3. The sum of their squares is equal to 504. Find the numbers.
Okay, ratio 1.2.3. How do we represent the numbers themselves?
Since they're in that ratio, we can represent them using a common multiplier. Let's call it x. So the numbers are 1x, 2x, and 3x, or just x, 2x, and 3x. Now the problem states the sum of their squares is 504. So we write the equation x2 plus 2 by 2 plus 3 by 2 equals 504.
Okay, now solve for x.
Simplify the squares first. by 2 plus 4 by 2 plus 9 by 2 equals 504. Combine the terms. 1 plus 4 plus 9 by 2 equals 14 by 2, so 14 by 2 equals 504. Divide by 14 by 2 plus 504, 14 equals 36. If by 2 equals 36, then x equals x up as 6. We usually take the positive root in these contexts. Now we know x6, we can find the three numbers. First number is x, second number is 2x, 2 times 6 equals 12. Third number is 3x, 2 times 6 equals 18. So the numbers are 6, 12, and 18. This shows how ratios combine with algebra.
Okay, that makes sense. What if we have several ratios linking different things, like A to B, then B to C, C to D?
Example 3, combining multiple ratios. Good question. Let's say A, B equals 3, 4, B, C equals 8, 9, C, D equals 15, 16. And we want to find the overall ratio A, B, C, D.
How do we chain them together?
The key is to make the linking terms equal in the ratios you're combining. First, let's find ABC by combining AB and BC. The linking term is B. In AB, B is 4, in BC, B is 8. We need to make the B value the same. The least common multiple of 4 and 8 is 8. So we multiply the first ratio, AB equals 3.4 by 2, 3 day 2, 4 dying 2 equals 6.8. Now we have AB equals 6.8 and BC equal 8.9. Since B is 8 in both, we can combine them directly. ABC equals 6.8.9.
Okay, step 1 done. Now bring in CD.
Right. We have ABC 6.8.9 and CD equals 15.1. The linking term now is C, and ABCC is 9, and CDC is 15. We need to make the C value the same. The LCM of 9 and 15 is 45. Multiply the ABC ratio by 5, since 9 by 5 equals 45. 16 by 5 equals 45.48. Now C is 45 in both adjusted ratios, so we can combine everything. ABCD equals 30.40, 0.45, 0.48.
Wow, that's a systematic way to link them all. Useful for tracking relationships across different groups. What about those proportionals?
Example 4, finding the third proportional. Find the third proportional to 15 and 20. Remember, three quantities A, B, C are in continued proportion if A, B, B, C. Here, A15, B20, and we're looking for C. The third proportional, let's call it X. So we set up the proportion 15.20.20X.
How do we solve that?
The fundamental property of proportion is that the product of the extremes, the outer terms, 15 and x, equals the product of the means, the inner terms, 20 and 20. So 15x equals 20 times 20. 15x was 400. Solve for x, x equals 415, which simplifies to 803. That's the third proportional.
That's the mean proportional.
Example 5, finding the mean proportional. Find the mean proportional between 3 and 75. Here we're given A3 and C 75, and we want to find the mean proportional in the set of A, B, B, C. Let the mean proportional be x, so 3.x, x, 75. Product of extremes equals product of means. 3 times 75 is x pi is x. 225 is also 2. Solve for x, x, 225 equals 15. So 15 is the mean proportional between 3 and 75. 3.15 is 1.5, and 15.75 is also 1.5.
Got it. One more type, inverse proportion.
Example 6. Inverse proportion, men and days. If 15 men reap a field in 28 days, in how many days will 5 men reap it?
Fewer men should take longer, right? So it's inverse.
Exactly. As one quantity men goes down, the other days goes up. For inverse proportion, the relationship isn't M1, M2 is D1, D2. It's M1, M2 equals D2, D1, or more simply, the product is constant. M1, D1 equals M2, D2. Given M1 equals 15 men, D1 equals 28 days, M2, we call it X. Set up the equation. 15 minus 28 equals 5x. Now solve for x. X equals 15 minus 28, 5. Simplify equals 155. That's 28 equals 28. Just 28 equals 84 days. It makes intuitive sense. 1/3 the men takes 3 times as long.
Perfect. Now, related to ratios and proportions, but maybe even more common in daily life, are percentages. It feels like percentages are everywhere. How did this per hundred way of looking at numbers become such a universal tool for understanding comparisons and changes?
It really is ubiquitous, isn't it? And it's precisely because of its universality and how easily it allows comparison. The term percent literally means for every 100. So a fraction whose denominator is 100 is called a percentage, and the numerator of that fraction is known as the rate percent. We simply write x% as shorthand for by 100. It standardizes comparison. Saying 20% off is immediately understandable whether the item costs $10 or $1,000 because it's relative to the whole, the 100%. It puts everything on the same scale per 100.
Can we see some quick examples?
Sure. A student gets 60% marks in all subjects. If the maximum marks for the exam are 500, what are the total marks obtained? Here we need to find 60% of 500. Of usually means multiply in these cases. So marks 6100, but 500.6500 equals 300 marks. 30% of a number is 144. Find the number. Let the unknown number be x. Then 30% of x is 3100x. We're told this equals 144. So 3100x equals 144. To find x, multiply both sides by 130. X equals 130, 130, 144, 103, 10, 48, 10. 10 was 480. The number is 480.
Okay, basic calculations. Are there common scenarios or theorems for percentages that act as useful shortcuts?
Yes, absolutely. Understanding the logic behind these can save a lot of calculation time in common problems. Theorem 1, comparative percentage change. This helps translate percentage differences between two perspectives. If A is R% more than B, then B is less than A by R, 100 plus R, A 100%. Notice the denominator is 100 plus R. Example, A's income is 20% more than B's income. By what percent is B's income less than A's income? Here, R20. So B is less than A by 20, 100 plus 20. I100, this gains 16, maybe 100. You're saying it's not just 20% less.
No, because the base for comparison changes.
Yeah.
Similarly, if A is R% less than B, then B is more than A by R, 100R, A 100%. Notice the denominator is 100R now. Example, if the price of fuel is reduced by 20%, R how much percent should consumption be increased so the total spending stays the same? We use the second formula, 20, 120, after 780 as 114 as 100% to compensate for a 20% price drop.
That's very useful for budgeting. Okay, what else? Theorem 2, percentage of one quantity relative to another. This sounds complex, but is simple. If A is X% of C and B is Y% of C, then A is simply XY% of B. You just compare the percentages relative to the common base C. Example, two numbers are respectively 20% and 25% of a third number. What percentage is the first number of the second? Here, X20, Y25. The first is 20, 25, 100% of 45, 100% is 80% of the second. Theorem 3, successive percentage changes. This is crucial for tracking things like investments or population growth over multiple periods. The key is that each change applies to the new value, not the original. If an initial value P undergoes successive changes of past X%, 80%, past 80%, the final value is P, A into 1, past by 100, A into Y, and a Z100. Use A plus may for increases, may for decreases. Example, the population of a town is 10,000. It increases by 10% in year 1, decreases by 20% in year 2, and increases by 30% in year 3. What's the population after 3 years? Example, pop 9,000, 80 plus 1000, 100 plus 3000. Example, pop 10,000, 880, 100, 880, 100, 80, 100, 800, 30, 100. Example, pop Henry 1000, U 1.1, pi algebra 0.8, twice 1.3 equals 11,440. Notice it's not just 10%, 20% plus 30% plus 20% overall. The compounding matters.
Right, the base keeps changing.
Exactly. And that leads to theorem 4, net change from equal, increase, and decrease. This is a classic. If a value is first increased by X% and then immediately decreased by the same X%, the net result is always a decrease.
Always. Why?
Because the X% increase is calculated on the original smaller base. The X% decrease is then calculated on the new larger base. So you lose more on the way down than you gained on the way up. The net decrease is always given by 200%.
Yeah.
An example, if salary is increased by 15% and then decreased by 15%, what's the net effect? Net effect is a decrease. The percentage decrease equals 15 to 100 equals 225. 100 equals 2.25%. The final salary is 2.25% lower than the original.
That's a good one to remember. Seems counterintuitive at first.
It does. And there are other specific theorems, like Theorem 5 for calculating maximum exam marks if you know the pass percentage and how many marks someone failed by, or Theorem 6 for figuring out the percentage of students passing both subjects if you know the failure rates in each and in both. They all rely on these core percentage logic principles.
Okay, moving towards wrapping up our core concepts, let's talk about averages. How do we get a sense of the typical value within a set of data, or analyze changes within groups? Averages seem fundamental to summarizing information. We use them constantly, from sports stats to weather reports to economic indicators.
You're absolutely right. An average, in its most basic sense, is simply the ratio of the sum of a set of quantities to the number of quantities in that set. It gives us a single value that aims to represent the center or typical value of that data set. It smooths out the highs and lows to provide a general idea. For example, if a cricketer scores 35, 47, and 37 runs in 3 different innings, his average runs for those innings would be the total runs divided by the number of innings. Average of 35 plus 47 plus 37.3 equals 117.3 equals 39 runs. This simple calculation, sum divided by count, gives us that single number, 39, to describe his typical performance across those games. It's a really powerful summary statistic.
Sum divided by count, the basic mean average. Are there useful shortcuts or theorems involving averages, like with percentages?
Yes, there are several handy theorems that provide quick ways to solve common problems involving changes in averages, without always needing to calculate the full sums. Theorem 1, average when a new member is included. This formula helps you efficiently figure out the value, like age or score, of a new member added to a group based on how the average changed. If the average of X members is Y, and when one new member is included, making X plus 1 members, the average becomes Z, then the value of the new member is given by New total sum. Old total sum, which simplifies to z plus xzy.
Let's see that with numbers.
Example. The average age of 30 boys in a class is 14 years. When the class teacher's age is included, the average age becomes 15 years. Find the teacher's age. Here, x equals 30, original number of boys, y equals 14, original average age, z equals 15, new average age of the new member teacher equals z plus x, zy equals 15 plus 30 equals 15 plus 30, 1 equals 15 plus 30 equals 45 years. This formula lets us find the teacher's age directly without calculating the total age sum before and after.
Much quicker. Is there a similar one for when someone leaves?
Yes, theorem 2, average when a member is excluded. It follows similar logic. If the average of x members is y, and when one member is excluded, leaving x1 members, the average becomes z, then the value of the excluded member is old total sum, new total sum, which simplifies to y plus x1 yz, or equivalently z plus xyz using the original values might be simpler sometimes. Let's stick to the source's formula. Z plus xyz might be misremembered. Let's use the total sum logic. Excluded value xy, x1z. The source provided z plus xyz. Let's verify that with an example. Average of 3 people, x3 is 20, y20. Total 60. Remove 1, average of 2, x12 becomes 18. New total 36. Excluded 60, 36, 24. Using formula 18 plus 3, 23, 2. It gets 18 plus 6, 24. Yes, it works. So age of excluded member is z plus xyz years.
Okay, a formula for adding and removing members. What about analyzing groups within a total, like pass-fail in an exam?
Theorem 3. Average marks for passed and failed candidates. This is useful when you have an overall average, but also averages for specific subgroups, like those who passed versus those who failed. If the overall average marks of X candidates is Y, the average marks of the passed candidates is A, and the average marks of the failed candidates is B. Then you can find the number who passed or failed. Number of students passing equals XYBA. Total, overall average, failed average, passed average, failed average, passed average, failed average, number of students failing, XYAB. Total, passed average, overall average, failed average, part.
Yes.
Example. The average marks obtained by 120 candidates, X120 in an exam is 35, Y35. If the average marks of passed candidates is 39, A39, and that of failed candidates is 15, B15, what is the number of students who passed? Number passed equals 120, 39, 15. Number passed equals 120, 24. Number passed equals 2424 equals 100. So 100 students passed and therefore 20 failed. This method avoids setting up simultaneous equations.
Very efficient. What about replacing someone in a group?
Theorem 4. Average change due to replacement. This helps find the value of a new person or item that replaces an old one based on how the average changed. The average age of X men changes by Y years, can be increase or decrease. When one man, whose age is Z years, is replaced by a new man, the age of the new man is ZXAY. Use plus if the average increased, use day if the average decreased.
Yes.
Example. The average age of 4 men X4 is increased by 3 years, Y3, when one of them, aged 40 years, Z40, is replaced by another man. Find the age of the new man. Since the average increased, we use the plus sign. Age of new man equals Z plus X times YX by 3 plus 40 plus 12 equals 52 years.
Yeah.
The new man must be 52 years old to cause that increase in the average.
Okay. And finding a missing value if you know parts of the average?
Theorem 5. Finding a missing value in a series. Yes, if you know the overall average and the averages of subsections, you can find a specific missing number. Example. The average of 11 results is 30. The average of the first 5 results is 25, and that of the last 5 results is 28. Find the value of the sixth number. The total sum of all 11 results is average x number 11 x 30 equals 330. The sum of the first 5 results is 5, last 25 equals 125. The sum of the last 5 results 7 through 11, is 5 by 28 equals 140. The sum of the first 5 and the last 5 is 125 plus 140 equals 265. The sixth number must be the difference between the total sum and the sum of the other 10. The sixth number must be the difference between the total sum and the sum of the other 10. Sixth number puts total sum of first 5 plus sum of last 5. The sixth number must be the difference between the total sum and the sum of the other 10. Sixth number is 30, 230, 65 equals 65. The sixth number must be the difference between the total sum and the sum of the other 10, so the sixth result must have been 65.
That makes perfect sense. Okay, finally, let's look at how these numbers apply in a really crucial financial context. The concept of interest, specifically simple interest. This is fundamental to understanding loans, savings, investments, core personal finance stuff.
It truly is. When money is borrowed or lent, very often an additional sum has to be paid back along with the original amount. This extra money is called interest. The original sum that was lent or borrowed is known as the principal. Interest is typically calculated at a specific rate percent per annum, meaning a certain percentage for every 100 currency units, like dollars or pounds, lent per year. This rate is key. Simple interest is the most basic form. It means the interest is calculated only on the original principal amount for the entire time period. It doesn't compound, meaning you don't earn interest on previously earned interest.
Just interest on the initial amount. How is it calculated?
The basic formula for simple interest, SI, is very straightforward. SI is backment PERET 100, where P, principal, the initial amount, R, rate, the percentage per year, and T, time, the number of years.
Okay, P times R times T divided by 100.
Example.
Find the simple interest on R's 400, P400 for 5 years, T5 at 6% per annum, R6. SI, 400 I6 by 5, 100. SI equals 400, 100. S6 times 5 equals 6 minus 5 as 4 as 30 equals 5 and 20. So the simple interest earned or paid would be Rs 120. The total amount repaid would be principal plus interest equal 400 minus 120 equal 520.
Simple enough. Are there theorems for simple interest too?
Yes, a few useful ones for common simple interest problems. Theorem 1, time for money to become in times. This helps you quickly find out how long it takes for investment to grow by a certain multiple at a simple interest rate without needing the principal amount. The time t it takes for a sum of money to become times self, e.g. N2, N3, at a simple interest rate of R% per annum is given by Tn1 at 100R.
Why? Because to become n times itself, the interest earned must equal n1 times the principal. For example, to double n2, the interest must equal 1 times the principal. To triple n3, interest must equal 2 times the principal. Example. In how much time does an amount of money become 4 times itself, n4, at a simple interest rate of 5% per year, R5? T equals 4, 1, and N105, T equals 3, and 105 equals 305 equals 60 years. It would take 60 years to quadruple at 5% simple interest.
Okay, that's handy. What if you know how long it takes to reach one multiple and want to know how long for another?
Theorem 2, change in time for n multiplier. This relates the times taken to reach different multiples under the same simple interest rate. If a sum becomes n1 times itself in t1 years, then the time t2 taken for it to become n2 times itself is given by t2, n21, n11, at1. Example, a sum of money trebles itself n1 3 in 14 years, t1 14, and how many years will it become 5 times itself, n2 5? Example, t2 0 5 1 through 1 at 14. Example, t2 equals 4 2i 4 2 up to 14 equals 28 years. It will take another 14 years, 28 total, to reach 5 times the original amount.
That shows simple interest growth is linear.
Exactly. Constant amount per year. There are also theorems, like Theorem 3, for finding the principal if you know how much more interest is earned due to an increase in the interest rate over a certain time. And Theorem 4, which provides a formula to calculate the fixed annual payment needed to completely pay off a debt, including simple interest, over a set number of years. Example for Theorem 4. What annual payment will discharge a debt of Rs 848 in 4 years at 4% per annum simple interest? Using the specific and slightly complex formula for this, the answer comes out to be Rs 200 per year. This kind of calculation is vital for understanding loan repayments.
Wow. What an incredible journey through the basics of math. We've gone from the very definition of numbers and their different types, through the power of equations to solve for unknowns, and then into these really practical applications in ratios, percentages, averages, and even financial concepts like simple interest. We've really seen how these foundational pieces fit together like a beautifully designed, coherent system.
It truly highlights that these aren't just abstract rules stuck in textbooks, are they? Understanding these basics is really about equipping yourself with the analytical tools for clearer thinking, more efficient problem solving, and just better decision making in so many areas of life. These concepts, which seem simple on the surface, are genuinely the bedrock upon which vastly more complex ideas are built, everything from advanced engineering and quantum physics to sophisticated economics and financial modeling. The real aha moments often come when you realize the sheer elegance and the internal consistency within these mathematical systems and how effectively they describe and help organize the world around us.
So, thinking about all this, what does it mean for you, our listener? As you move forward from this deep dive, maybe consider this. If these fundamental mathematical concepts, some of which were discovered millennia ago, can still so powerfully organize and predict aspects of our everyday lives from, the curve of a thrown ball to the balance of your checkbook, what else might they be quietly explaining about the universe? Think about how a deeper understanding of numbers and the relationships between them might unlock insights in fields you never even expected, maybe even in areas that feel totally far removed from traditional math problems. Where else are these underlying principles just waiting to be fully appreciated and applied in your own life or in the world you observe? That's definitely a question worth exploring.